Hey there. This is the first video in a series where we'll examine how computers work from the ground up. No personification, no hidden abstractions, and we're just going to build straight up from chemistry and physics. So let's get into it. This video is about semiconductors and transistors. And before we jump into the technical material, let's try to understand the motivation behind what we'll soon come to know as a MOSFET. Computers are information machines. Without a way of storing information, they really are just a dumb rock. Computers store information in its most fundamental form, which is the bit, short for binary digit. A bit is the amount of information gained when one of two equally likely outcomes occurs. We tend to think of bits as ones and zeros, ons and offs, heads or tails. Really, any binary classification stores one bit of information. With this in mind, we'll start off with a discussion of semiconductors, which will lead into transistors and will all tie back to the information storage and manipulation. Semiconductors, which are semiconductors. Let's understand this word. What is a conductor? It's a material that exhibits conductivity, of course. So, what is conductivity? It's an inverse measure of how much a material resists electrical current. On the low end of the conductivity spectrum are insulated materials like glass and ceramic, and on the high end are conductors like copper and gold. Semiconductors, it would follow, lie somewhere in the middle. Free electrons lend to a material's conductivity. In other words, if a material has an abundance of free electrons, it's likely to be a conductor. If it has very few free electrons, it's likely an insulator. So, what is a semiconductor then? Well, of course, it's just a material with a medium amount of free electrons. No, I'm just kidding. That's a stupid definition. What we typically mean by semiconductors is actually a material whose conductivity can be tuned and manipulated in precise ways. So, let's take a look at some of these materials to understand better. Zooming into the periodic table, there are three groups of elements that concern us. These are groups 3, 4, and 5. Recall that the group number denotes how many electrons are present in the atom's valence, or outermost shell. Group 4 elements have 4 valence electrons, which is exactly half of the shell's maximum capacity. This lends to some interesting properties and gives these elements the title elemental semiconductors. A brief sidetrack. I want to mention that it turns out we can mimic elemental semiconductors by combining group 3 and 5 elements. These would be called compound semiconductors. Gallium nitride is probably the most common of these, and it has the benefit of being able to withstand extremely adverse temperatures and pressures. It also tends to be much more expensive than elemental semiconductors, which we'll look at for the rest of the video. So let's put groups 3 and 5 aside for now, and we'll revisit them later. This leaves us with 6 choices for the material. So let's play the elimination game. This one's radioactive, this one's toxic, and this one's really, really expensive because it's literally just diamond. This one forms a metallic lattice that acts too much like copper or gold. And this one's theoretically feasible, but it's quite rare naturally, so it's hard to harvest. And this leaves us with only one good choice, and that's silicon. As it turns out, silicon is a really good choice. It's incredibly abundant in the Earth's crust, it's relatively easy to refine, it exhibits uniform lattice structure, and it has an appropriate band gap needed for efficient semiconductor behavior. Before we move on, I mentioned in brief passing that silicon is relatively easy to refine. This is because it can be pulled out from silicon dioxide, aka beach sand. The manufacturing process for ultra-pure silicon is very interesting indeed. And by the way, ultra-pure silicon doesn't mean 99% or 99.9% or anything even really close. It's so pure that we tend to denote the number of nines present in the number. State-of-the-art manufacturing processes can achieve 99.999999999% pure silicon, or as it's called, 11 nines. We'll see why this level of purity is so important later on. Back to silicon for now, I want to talk about silicon's lattice structure because it's very important to how it behaves as a semiconductor. Recall that silicon has 4 valence electrons, meaning it will form 4 covalent bonds with its neighboring atoms. This is just a 2-dimensional illustration, but in 3 dimensions it would have a tetrahedral shape. In this form, silicon acts basically like an insulator, because there are little to no free electrons present. is because all the electrons are used to bond the silicon together. This is where we'll reintroduce groups 3 and 5 from the periodic table, because they're how we can turn this insulating lattice into a semiconductor. Let's choose phosphorus as an example. Phosphorus sits right next to silicon on the periodic table, so its size and behavior is quite similar. It's so similar, in fact, that we can sneak a little bit of phosphorus into the silicon lattice without disrupting the structure at all. Now, the difference is that phosphorus brought along with it a free electron that doesn't participate in any bonds. It's worth noting that the net charge of the lattice didn't change at all because the phosphorus also brought along with it a proton. Now, conversely, what happens if we add a group 3 element like aluminum into the lattice? Once again, it fits in without causing any problems, but now there's a hole where an electron used to be. Surrounding electrons that are excited can jump to fill that hole, effectively creating a positive mobile charge. This process of adding slight impurities to the lattice is known as doping. And with modern manufacturing techniques, we can finally control how much of a group 3 or 5 element is added to the silicon, effectively gaining complete control over its conductivity. So, this gives us the semiconductor material. Now, how do we build a transistor out of it? First, some quick terminology. A lattice doped with a group 5 element is called an n-type lattice because its mobile charges are negative electrons, whereas a lattice doped with a group 3 element, such as aluminum, is called a p-type lattice because its mobile charges are positively charged holes. So let's consider what happens when these two types of lattices are placed side by side. What happens at the boundary is that the free electrons from the n-type lattice will move to fill the holes in the p-type lattice. This forms what we call a depletion layer. And what's been depleted? All of the mobile charges. So this means that the entire block will strongly resist current flow because there's no way for electrons to flow through the depletion zone. Consider now what would happen if we add an electric field to the picture. The negatively charged electrons, of which there's an excess in the depletion zone, will flow against the field, effectively shrinking the zone and once again allowing current to pass through the block. This is the concept that allows transistors to operate. So now let's take a look at how they're implemented. What you'll typically see is something that looks like this. There will be two p-type lattices called the source and the drain. These are the two terminals where current enters and exits the transistor. Between them, there's an n-type lattice that we call the body of the transistor. The source terminal and the body are shorted to ensure that they have the same potential. The region between the source and drain is called the channel, and above this channel sits the metal plate, called the gate, insulated from the body by an oxide insulator. Hence we get the very long name, metal oxide semiconductor field effect transistor, or MOSFET for short. When the correct voltage is applied to the gate, the depletion layers between the two lattices shrink, allowing current to pass through. When no voltage is applied, the depletion layer returns, and current is blocked once again. This is it. This is now a very tiny, very fast, and very reliable switch. Before I close though, I should mention that this is only one of 4 major types of MOSFETs. You can achieve another type by simply switching around the N and P-type lattices, which will result in the same functionality. We call the one on the left an N-type MOSFET because it has an N-type channel, and vice versa. Notice how the default state for these two transistors is off. We can alter that to get the other two types. If we extend a similar lattice type between the source and the drain, now current will flow by default, but will be halted when the correct voltage is applied to the gate. When a MOSFET is off by default, it's called an enhancement MOSFET. When it's on by default, it's called a depletion MOSFET. So hopefully this video was not too cumbersome. If you're interested in seeing more of the math that determines how much current flows through the transistor, depending on many different factors, let me know in the comments and I can make that video as a sequel to this one. Also, if you have any questions or if anything was confusing, I totally understand. This is a very tough topic, but feel free to drop it in the comments and I'll respond to the best of my ability. Otherwise, that's all for today, and take care.